This is 6.2.1.3. In the past few slides, we examined how to compute the DTFS of a complex exponential using this analysis equation directly. And of course, we can use a computer to write this, and we generate samples and we compute CKs directly. However, in this particular example of complex exponential, we really do not need to evaluate CKs using the analysis equation. We can actually instead just inspect xn and we can get the CK's values directly. And why is this so? Well, let's study xn first. This is our xn, and this is the equation that we begin with amplitude 3 with omega equals to 0.2 pi and with phase shift of minus 0.5 pi. We can rewrite this equation by breaking down this block into two different parts. One exponential multiplying by the exponential. We then bring these guys in front. So this is 3e, well, I and j are the same, and then minus 0.5 pi and then 3e of these frequencies. So what are we identifying with now? Is that we are having a complex number 3e with phase of minus 0.5 pi multiplying by this complex exponential, and omega naught in this particular case is we first analyze xn and realize that n equals to 10 is the period, so 2 pi over n is 0.2 pi, so we just write as omega naught, and omega naught here is the fundamental angular frequency of this sequence. So this equation and this equation are the same, it's just written as different form, where in this particular equation 3e j minus 0.5 pi represents the complex number multiplying by this complex exponential. When you realize this, you immediately realize that isn't this exactly the same as this guy, where n is, let's say, 10 now and k equals to 1. So this is the complex exponential that is rotating with angular frequency 2 pi over 10, and ck is this number, a complex number with amplitude 3 and phase shift minus 0.5 pi. And what is k? Well, to get this omega naught, we set k equals to 1 because it came from setting n equals to 10 first. When we set n equals to 10, there's 2 pi over 10, you got 0.2 pi. To get this as 0.2 pi, we set k equals to 1. So that's why ck is this value over here. And then immediately, just by comparing the inverse, which is the synthesis equation, we can find ck. So what's the trick again? Well, since we know that xn is a complex exponential, we can use inspection. To do inspection, what do? We are actually looking at how the synthesis equation, so this is a synthesis equation, or sometimes called the inverse DTFS, we cast our xn into this form. And when we cast our xn into this form, it is a complex value multiplying by a complex exponential rotating at 2 pi over n times k. So what we do is that we basically break our equations into two parts. One of them is the rotating part, which is this guy here, and the other one is just a phase shift. So we move the phase shift in front, multiplying by amplitude, and we now have a complex exponential. We need to get omega naught k to be exactly 0.2 pi, and then we have to figure out what is n and what is k. Once we have figured it out, we will now get the value of ck. Whatever this value is ck. So this is the example of DTFS for this complex exponential by inspection. Thank you.